Welcome to our class on Thermodynamics Basics 3. In this class, we are going to study two important things. One is entropy and adiabatic change. These have got very simple daily significance. In our daily lives, we see innumerable aspects of entropy and adiabatic changes. Actually, I just did because this is the basics, so I will give only some sort of basic definition of it and one or two, three examples of daily in the daily life how these two are important in our life. And as far as our crops are concerned, whether it is cereals, pulses, oilseeds, commercial crops or plantation crops, or even for that matter animals, applications in agriculture metrology in the days to come, we try to understand. Now first let us see what is entropy. Entropy is very simple. The thermal property of a body, is the thermal property of a body which remains constant. The thermal property of a body which remains constant during an adiabatic process. This is an adiabatic process. That adiabatic change we study later on. During an adiabatic process, when no heat is when no heat energy is given to or removed from it. So the thermal property of a body, the thermal property of a particular body which remains constant. So during an adiabatic process, when no heat energy is given to or removed from it, that's what we call it as entropy. As far as its the statistical definition is concerned, it is further simple. According to statistical definition, what we can say is that entropy is the product of Boltzmann constant K and natural log of thermodynamic probability N, we call it as basic physics. This is the basic physics definition. Of course, the dimensions of entropy, usually we define it by S, capital S. So X per degree Kelvin or joules per X per degree Kelvin or joules per degree Kelvin, whatever the dimensions of S, depending upon MKS, CGS, S, different systems. Now, see what is an example of it. I would like to tell an example of campfire. If you take campfire, the solid, when we burn the solid wood, what happens? The solid wood, while burning, some dust, some gases, some smoke, some ash, all these things will dissipate the energy, heat energy which is in the solid wood. So this energy has got more impact as compared to the solid wood itself. It's a classical example. Similarly, when you take in our daily lives, if you take a gas cylinder, when you open the gas cylinder, the gas comes out. It is a irreversible process. However, when you try to put a small piston to it, or when you try to put it back, so it can be reversed back. Once we allow it, it is irreversible change. Once we allow with a piston or something, we try to control it, then it is a reversible process. So similarly, when you take some ice cubes, small ice cubes, you take it, when you keep them on a furnace, they get melted. Once they get melted, the furnace gets cooled up, but with small energy we cannot get that ice back. So in daily life, innumerable examples of entropy are there. Once again, for your academic interest, I would like to read that simple. The thermal property of any body, of a body which remains constant during an adiabatic process when no heat energy is given to either given to or removed from it. That's what. So again, further explanation I will give. The entropy of a system is equal to sum of one or two or three subsystems, if we take subsystem. Similarly, the entropy is a measure of randomness or disorder. It is a measure of randomness or disorder also, of any object in a system. Disorder, randomness, these are complementary to each other. Now, this is more or less internal and unavailable energy of a system resulting from internal movement of the molecules. Unavailable energy, that is, in other words, what we can say is that it is a measure of the system's thermal energy per unit temperature that is unavailable for doing useful work. Okay, doing useful work. See, even in case of a watch also, it has got energy in it. Okay, in it. Now, so because work is obtained from ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of any system. So this is what is entropy. Classical examples I had given to you: a campfire, you can say ice cubes on the furnace, or you can say some gas cylinder, what not, innumerable example in the daily life we can say it. Similarly, and as our advances class, in the advances classes, how we can apply this entropy into even in the frost management, in different management techniques. Okay, I don't want to limit one or two. In different management techniques, tools, services of agricultural metrology, entropy is extensively used, that we discuss in the days to come. Now let us go straight to a small this particular adiabatic change. Adiabatic change I have already. Please subscribe to my channel. Agronomy farmers and road development. They are in the basics of solar radiation, temperature, humidity, pressure, wind. So I have given what is adiabatic change and everything. But however, pure physics point of view, thermodynamics, from the thermodynamics point of view, I would like to enlighten you what is adiabatic change. When a change in the pressure and volume of a substance takes place, but no heat is allowed to enter or leave it, then the change is said to be adiabatic. Once again, for your academic interest, I will tell, when a change in pressure and volume of a substance takes place, but no heat is allowed to enter or leave it, the change is said to be adiabatic. What exactly does it mean? I would like to tell. Before that, we try to understand what is isothermal. Once you understand what is isothermal, then it is easy to understand adiabatic. So, in the temperature, that's why I am requesting you, please subscribe to my channel, Agronomy, Farmers and Road Development. There I had explained to you what is adiabatic lapse rate, dry adiabatic lapse rate. Now I am standing in the troposphere. In the troposphere, what happens? As the height increases, the temperature goes on decreasing. At what adiabatic lapse rate? It is 10 degrees centigrade when the atmosphere is presumed to be dry, completely dry. When atmosphere is considered to be in the troposphere completely wet, the wet adiabatic lapse rate is 5 degrees centigrade. Usually, either it will never be completely dry or completely wet. That's why average adiabatic lapse rate is 6.5 degrees centigrade for every kilometer. That's what I would like to say. In the troposphere, particularly over the equators. As we go away from the equator, of course, the troposphere size decreases. Near the equator, it is around 15 kilometers, I told. Now, see, it has got such a significance, wonderful significance, and even in our agricultural meteorology for application of adiabatic changes into the crops, into the plantation crops, into agriculture crops, into animals, whatnot, even in the forestry, we have innumerable examples of large-scale applications of adiabatic change are there. Once again, for your academic interest, I would like to say that an adiabatic change is defined as when a change in pressure and volume of a substance takes place, but no heat is allowed to enter or leave it. The change is said to be adiabatic. Now, what exactly does it mean? Through isothermal concept, I would like to explain to you by using the first law of thermodynamics. This is the thermodynamics basis. On the basis of first law of thermodynamics, what is isothermal? I will try to explain to you in 1 or 2 minutes. What is it? Very simple. Isothermal change, when a change in the pressure and volume, of a substance takes place, but the temperature remains constant, the change is said to be isothermal. First condition. When a gas is compressed suddenly, some heat is produced, but if the compression is slow, then the heat produced is removed at once. Okay, so that the temperature remains constant. This is also isothermal. Now, another example. Similarly, when a gas is allowed to expand suddenly, what happens? The work is done by the gas and some heat is absorbed. The work is done by the gas. So, some heat is absorbed from external sources. Now, if heat is continuously supplied from the outside so that the temperature remains constant, again the change is said to be isothermal. Now, let us apply the first law of thermodynamics. What the first law of thermodynamics says? Work done is directly proportional to heat produced, W is proportional to H, W is sigma T, sigma H Stefan Boltzmann constant. That's you know it. Now, when we apply the first law of thermodynamics to this isothermal change, then in an isothermal change, the temperature is kept constant by adding heat or taking away from the substance. First condition. Second condition, as there is no change in temperature, there is no change in the internal energy. As there is no bits will come in the basics, you know. That's what I would like to impress upon you, that you should understand. As there is no change in temperature, there is no change in internal energy, or what is happening in an isothermal change, or process, or you can say in isothermal change, process or transformation, heat added or subtracted is equal to work done by the gas or work done on the gas. Work done by the gas or work done on the gas. Okay, this is of Boyle's law also, we can say from this inference through Boyle's law also. I would like to impress upon you that for a perfect gas, isothermal change is represented by Boyle's law, okay, given by the equation PV is equal to constant. So this is what I would like to tell you from adiabatic change from the viewpoint of thermodynamics. Similarly, what is of course adiabatic change, when of course I have given the definition, two systems we will take it. Two systems. What are these two systems? Okay, first one, if no heat is taken away, the temperature will rise. In a system, what I explained 2 minutes back, if no heat is taken, the system temperature will rise. If no heat is supplied, the temperature will fall. These two conditions when we take. Hence, in an adiabatic change, the temperature does not remain constant and no heat from outside is supplied to the system or taken from it. Now, in that case, what will happen? If it does not mean that, please remember, bits will come here. It does not mean that heat content of the system remains constant. It does not mean that heat content of the whole system remains constant. We should not presume that heat content is constant. Why? Again, let us go back to half minute before. If no heat is taken away, the temperature will rise. If no heat is supplied, the temperature will fall. These two conditions if you take, in an adiabatic change, the temperature does not remain constant and no heat from outside is supplied to the system or taken away from that. Now, so let us see a classical example. When a gas is allowed to expand, see a gas cylinder you take, from the gas cylinder, there is a gas in it. When you allow it to expand, what will happen? Now that example is that when a gas is allowed to expand, it does external work and the energy for this purpose is drawn from the heat energy of the gas itself. Okay, the heat energy of the gas therefore decreases. What we said in the statement, it does not mean that heat content of the system remains constant. That's why I am telling this example. When a gas is allowed to expand, it does not, of course, it does external work and the energy for this purpose is drawn from the heat energy of the molecules of the gas. Otherwise, the heat energy of the gas therefore decreases. Now, second situation, when the gas is compressed. First situation, when the gas is allowed to expand. When the gas is allowed to compress, work is done on the gas. Work is done on the gas and energy gained appears as heat energy. The heat energy of the gas therefore increases. In the earlier case, the heat energy decreases. In this case, heat energy increases. Now, let us see from the thermodynamic point of view, or let us conclude it according to first law of thermodynamics. During an adiabatic process, no heat enters or leaves. That's what. Adiabatic change, when a change in pressure and volume of a substance takes place, but no heat is allowed to enter or leave it. Now, that is the situation according to first law of thermodynamics. I am trying to explain. During an adiabatic process, no heat enters or leaves the gas. Then when we apply first law of thermodynamics, therefore, in an adiabatic process, increase or decrease in internal, this bit will come. This is a good bit and the calculations using the simple first order differential equation or some basic matrix that advances it. This is only basic. That's why simply I am telling you increase or decrease in internal energy. Increase or decrease in internal energy is equal to work done by the gas or work done on the gas by using the first law of thermodynamics. Just for your academic interest, once again I assure you and more than assure you that in the advances, further examples I take, just this is the basics. So let us complete this particularly entropy and adiabatic change from first law of thermodynamics. That's why I told you the thermodynamic basics 3. Thanking you very much. May God bless you.